Welcome to Section 10, Grounding and Bonding. It is your responsibility to understand and apply all requirements of the Canadian Electrical Code Part 1, including those not addressed in the training. Do you want to know how to take the...
Hi, I'm Nathan, your subject matter professional for this learning. I will help you to understand and be able to apply the requirements of the section of the Canadian Electrical Code, Part 1.
The aim of this training is to provide new knowledge and to support the development of new skills that you can apply immediately to your job. The purpose is why you are taking this learning. To directly support the purpose, this learning has identified objectives. Here is what you will learn as you take this training. Save or print a copy of the Quick Reference Guide. It is located in Resources. Use this Quick Reference Guide to take notes and as a practical job aid for this code section.
The following terminology is included within this course. Equipotentiality, the state in which conductive parts have the same electrical potential throughout. Grounded conductor, the conductor of an electrical system that intentionally connects equipment to the earth through a grounding electrode. Impedance grounded system, an electrical system that is solidly grounded, where grounding conductors are connected to earth ground with no intentional added impedance in the circuit. Impedance system bonding jumper, a connection between the grounded site of an impedance grounding device and the non-current carrying conductive parts of the electrical system. Equipotential bonding involves joining together metalwork that is or may be earthed so that it is at the same voltage or potential everywhere. It is commonly used under transformer banks by power companies and under large computer installations. Separately derived system, an electrical system, the circuit conductors of which have no direct connection to circuit conductors of a supply authority system other than those established by grounding and bonding connections. Solidly grounded system, an electrical system that has one terminal bonded to its metal case by a grounding conductor. System bonding jumper provides the low impedance fault current path to the electrical supply source for the purpose of clearing the ground fault. Ungrounded system, an electrical system where no point of that system is intentionally grounded. Step voltage, the potential difference between 2 points on the Earth's surface, separated by a distance of 1 pace, assumed to be 1 millimeters in the direction of maximum voltage gradient. Touch voltage, the potential difference between a grounded metal structure and a point on the Earth's surface, separated by a distance equal to normal maximum horizontal reach. Equipotential plane, a surface having all areas or parts at a single potential to ground, such as wire mesh embedded in concrete to prevent a difference in voltage from developing. Grounding and bonding work together, however they are two different things. Bonding is used to equalize voltage potential differences, to reduce shock hazards between parts by connecting potentially conductive parts together. Grounding involves providing a low impedance, ground fault return path from the equipment required to be grounded back to the source of the electrical system, typically through the equipment grounding conductor routed with the branch circuit conductors. This path facilitates the operation of the fuse or circuit breaker to allow it to remove the faulted condition. In short, bonding means connected, while grounding means connected to earth. Grounding and bonding together provide the safety from shock hazards that is so important. In Section 10 of the Code, it is established that grounding and bonding can minimize the likelihood and severity of electric shock by establishing equipotentiality to prevent damage to property during a fault event as follows. By grounding an electrical system and bonding its associated equipment to establish a low-impedance connection between the grounded conductor and the non-current carrying conductive parts of the system to stabilize system voltage. An ungrounded system limits the magnitude of ground fault currents resulting from a single ground fault and minimizes the damage to equipment on the occurrence of single ground fault. Bonding interconnects the non-current carrying conductive parts of electrical equipment and the system grounded point, where one exists, with sufficiently low impedance to facilitate the operation of protective devices, and by establishing equipotentiality using equipotential bonding. Now that you know the difference between grounding and bonding, what is grounding? The first figure shows a ground fault on a grounded three-phase wire system. The minimum size of the grounded conductor as number 6-gauge copper or number 4-gauge aluminum. The second shows the ground fault current path on a three-phase wire system. The low impedance path for the ground fault is the grounded conductor between the service box and the supply transformer, as this is a metallic path where the resistance is fixed. Grounding is often referred to as the reference point in which a conductive body is connected to the earth. Electrical systems are to be connected to ground or earth through the grounding electrode. This will reduce the shock hazard between earth and the exposed non-current carrying metal of our electrical equipment. Rule 10-100 of the Code requires that there shall be no objectionable passage of current over a grounding conductor. Objectionable current is defined as a temporary current placed on the conductor due to abnormal conditions, such as a short circuit. There are three types of grounding electrodes with requirements. Those types of grounding electrodes are manufactured grounding electrodes, field-assembled grounding electrodes, and in situ grounding electrodes, forming part of existing infrastructure. Manufactured grounding electrode shall, in the case of a rod grounding electrode, consist of two rod electrodes spaced not less than 3 meters apart, interconnected with a grounding conductor sized as prescribed for grounding conductors, and driven to the full length of the rod, or a chemically charged rod electrode installed to the full length of the rod, or a plate electrode, be in direct contact with exterior soil at not less than 600 millimeters below grade level, or encased with thin bottom 50 millimeters of a concrete foundation footing in direct contact with the earth at not less than 600 millimeters below finished grade. Another commonly known grounding electrode is the field-assembled grounding electrode made of a bare copper conductor not less than 6 meters in length, sized in accordance with Table 43, and encased within the bottom 50 millimeters of a concrete foundation footing in direct contact with the earth at not less than 600 millimeters below finished grade, or a bare copper conductor not less than 6 meters in length, sized in accordance with Table 43, and directly buried in the earth at least 600 millimeters below finished grade. In situ grounding electrodes, which shall not be considered electrical equipment and must provide 600 millimeters or more below finished grade, a surfaced area exposure to earth equivalent to that of a similar manufactured grounding electrode. Where a local condition such as a rock or permafrost prevents a grounding electrode from being installed at the required burial depth, a lesser acceptable depth is permissible. Consult the authority having jurisdiction. Grounding electrodes must be separated by at least 2 meters between the grounding electrodes of building electrical wiring systems and the grounding electrodes of other wiring systems, such as lightning rod, communication, and community antenna distribution systems as required by the Code. This ensures that the area of influence of one electrode does not intrude upon that of another. Grounding electrodes must be interconnected with a conductor made of material prescribed for grounding conductors, sized as prescribed for grounding conductors, and protected from mechanical damage as required for grounding conductors, and in the case of lightning protection systems, interconnected in accordance with a conductor at or below ground level. To reduce the possibility of sparking, it is necessary to equalize potentials by bonding grounded metal bodies to the lightning protection system. Rule 10-108 requires down conductors to not be used for grounding electrical systems or equipment. The grounding electrode for a lightning protection system shall be dedicated for use solely by the lightning protection system. Any interruption of the bonding path to ground must be avoided. An automatic cutout or switch to be installed in the grounding conductor is not permitted, unless the opening of the cutout or switch disconnects all sources of energy. However, it may be necessary to install a device in the grounding conductor to eliminate the flow of objectionable current. These are sometimes referred to as tingle voltage filters used in agricultural areas. Only certain materials that are considered suitable for grounding conductors are permitted to be used. The list includes copper, aluminum, or other acceptable material, and permitted to be insulated or bare. The material to be used for grounding conductors is required to be resistant to or adequately protected against any corrosive condition existing at the installation, to ensure that under all conditions and after years of service the conductor and its connections continue to provide a low impedance path to the grounding electrode. It is important to know the different sizes of grounding conductors to limit the magnitude of current. Because the resistance of the grounding electrode and the earth or ground limits the amount of current that a grounding conductor can carry, particularly on low voltage services, Rule 10-114 of the Code does not require a grounding conductor size larger than number 6 gauge, if of copper, or number 4 gauge, if of aluminum, regardless of the size of the service. It is important that grounding conductors be electrically continuous throughout their length. When necessary, devices to control the effects of stray earth current, which shall be permitted to be connected in series with the grounding conductor. The figure on the screen shows the grounding connection for single-phase 3-wire AC, 3-phase 4-wire AC, and an ungrounded delta. Grounding conductors must also be protected from damage mechanically or by location. Raceways, or sleeves constructed of magnetic materials used to enclose grounding conductors, shall be connected to the grounding conductor at both ends. A grounding conductor installed in the same raceway with service conductors shall be insulated, except that an uninsulated grounding conductor shall be permitted where the length of the raceway does not exceed 15 meters between pull points, and does not contain more than the equivalent of 2 90-degree bends between pull points. Often, the connection to the grounding electrode is made and then forgotten, even though this connection and the bond between the grounding conductor and the identified conductor are probably the most important connections in the system. The intent is to ensure that the connection at the grounding electrode is, and continues to be, a permanent, low impedance and secure connection. The integrity of the grounding connection to the grounding electrode must be preserved under all conditions. This rule requires that the grounding conductor be connected to the grounding electrode where practicable, at an accessible location that allows for inspection, servicing, and testing, and assures a permanent connection to ground by any of the following means. To reduce the flow of DC current through the earth from a grounded DC system, it is required that DC systems that are to be solidly grounded, unless it meets the requirements for ungrounded or impedance-grounded systems. This can ensure that the connections to ground do not result in the earth becoming a return path for electrical current. The minimum grounding conductor size for a DC system to be grounded must be a number 6 gauge if of copper, or number 4 gauge if of aluminum. When the positive or negative conductors are larger than number 6 gauge if of copper, or number 4 gauge if of aluminum, the grounding conductor size cannot be less than the positive or negative DC conductor. Direct current flowing through the earth tends to seek out a metal ungrounded system, such as a municipal water system, which may suffer severe electrolytic corrosion when DC systems are grounded. To reduce the flow of DC current through the earth from a grounded DC system, it is required that it is solidly grounded. Have the grounding connections made at a single point, as close as practicable, to the supply source. This can ensure that the connections to ground do not result in the earth becoming a return path for electrical current. Because many components of AC systems are suitable only for voltages up to 150 volts, voltage levels on such systems must not exceed this limit. AC systems exceeding extra low voltage must be solidly grounded if the system incorporates a neutral conductor and it were run overhead outside, supplied by transformers energized from systems of more than 150 volts to ground, or supplied by transformers energized from ungrounded systems. AC systems exceeding the values prescribed by Section 10 of the Code shall be permitted to be ungrounded or impedance grounded, provided they meet the requirements for ungrounded systems or impedance grounded systems. In a typical service installation, a grounded conductor is on the supply side of the service. It is required to serve as a bonding conductor to carry fault currents between the service equipment and the source. The conductor of an AC system to be grounded must be one conductor of a single-phase, 2-wire system, the mid-phase conductor of a single-phase, 3-wire system, the mid-phase conductor of a multi-phase system having one wire common to all phases, one conductor of a multi-phase system having one phase grounded, and the mid-phase conductor of one phase of a multi-phase system. The grounded conductor of a solidly grounded AC system supplied by the supply authority shall be connected to a grounding conductor at one point, only at the consumer service. Have a minimum size as specified for a bonding conductor and for a neutral conductor when the grounded conductor also serves as a neutral, and be connected to the equipment bonding terminal by a system bonding jumper, and have no other connection to the non-current carrying conductive parts of electrical equipment of the supply side or the load side where the grounding connection is made. The grounded conductor of a solidly grounded separately derived AC system is required to be connected to the equipment bonding terminal by a system bonding jumper at the source, at the first switch controlling the system, or at the tie point, where two or more systems terminate at a tie point. Be connected to a grounding conductor as the same point on the separately derived system where the system bonding jumper is connected. Have no other connection to the non-current carrying conductive parts of electrical equipment on the supply side or the load side of the grounding connection. A separately derived AC system operating at 750 volts or less is permitted to be grounded by the system bonding jumper that is connected to the bonding conductor included in the primary supply. A portable generator assembly shall not be required to be connected to a grounding electrode if the generator has the neutral bonded to the frame. A mobile or vehicle-mounted generator shall not be required to be connected to a grounding electrode under the following conditions. The generator does not exceed a low voltage rated output. The generator has the neutral bonded to the frame. The generator supplies only electrical equipment installed on the vehicle, electrical equipment that is cord and plug connected through receptacles mounted on the vehicle or on the generator, or any combination of both. The conductive frame of the generator is connected to the conductive frame of the vehicle by an equipotential bonding conductor. The non-current carrying conductive parts of the electrical equipment are supplied by a circuit incorporating a bonding conductor. Time for an activity. Choose your response and then select Submit. The most common type of low-voltage system that can give advantages without the disadvantages is called the impedance-grounded system. Often these systems are referred to as high-impedance or resistance-grounded systems because of the addition of a neutral grounding device, usually resistors, in the grounding conductor of the transformer. When an electrical system is connected to an impedance-grounding device, it must be maintained by a qualified person. These requirements must also be monitored and meet certain conditions. Click each box to learn more. In the first figure, a neutral grounding device, resistance, is added in the return conductor to reduce the fault current level in the electrical system to no more than 10 amps. The second figure shows the ground detection system that must be added to an impedance-grounded system to indicate there is a ground fault on one phase. The third figure shows the path of the ground fault current when one phase is grounded. Provided the ground detection device can function as required for an ungrounded system, the system should be permitted to continue to operate. Several factors impacting system reaction to a ground fault include system voltage, ground fault current limits, whether the line to neutral loads are served, ability of the monitoring device to detect a ground fault on an ungrounded system on event of loss of continuity in the impedance grounding circuit. Table 17 concisely specifies the required action based on the numerous potential combinations of systems, types of fault, and monitoring device capabilities that can be encountered. Where impedance grounding devices are used, it is required that warning signs indicate when the system is impedance grounded. The maximum voltage at which the neutral may be operative relative to ground shall be placed at the supply source, the consumer service box or equivalent, and the supply authority's metering equipment. Conductors connecting the impedance grounding device to a system are required to be insulated for the nominal system voltage, identified as white or gray, routed as directly as practicable, not to be grounded, and sized to conduct the rated current of the impedance grounding device, and in no case less than number 12 gauge if of copper, or number 10 gauge if of aluminum, and be protected from damage mechanically or by location. It is also required that the grounded side of the impedance grounding device to be connected to the non-current carrying parts of the electrical equipment by an impedance system bonding jumper sized to conduct the rated current of the impedance grounding device, and in no case less than number 12 gauge if of copper and number 10 gauge if of aluminum. In an ungrounded system, it is required that DC or AC systems be permitted to be ungrounded if the system is equipped with suitable ground fault detection and maintained by qualified persons. On the occurrence of a single ground fault on one conductor, the ground fault detection can activate a visual or audible alarm to indicate the presences of the ground fault. The required alarm, and any extra alarms if installed, must be clearly labeled as to its purpose and clearly enunciated the status of the system to persons monitoring it, along with continual signaling until the condition is corrected. Extra low voltage DC or AC systems are permitted to be ungrounded without having to comply with the ground fault detection requirements specified in Section 10 of the Code. This figure shows the second ground fault has occurred on another line. The fault current now has increased as the fault is line-to-line fault, and two overcurrent devices need to trip to clear the fault. This can result in equipment damage due to the higher fault current level. Here is a short activity to apply what you just learned. Enter your response and select Submit. For safety reasons, there can be no connection between the grounding conductor and the system neutral where one is present. The grounding conductor shall connect the grounding electrode to the non-current carrying conductive enclosure of the supply source equipment of separately derived systems or the service box. Time for an activity. Choose your response and then select Submit. There are certain general requirements regarding bonding that must be adhered to. First, there shall be no objectionable passage of current over a bonding conductor. Next, any non-conductive coating, such as paint or enamel being used on conductive equipment, conduit, couplings, or fittings, must first be removed from any threads and other contact surfaces or penetrated to ensure a good electrical connection at the point of bonding. Where incompatible metals cannot be avoided at bonding connections, it is required that connections be made using methods or material to minimize deterioration from galvanic action. The installation of an automatic cutout or switch in the bonding conductor of a wiring system is not permitted unless the opening of the cutout or switch disconnects all sources of energy. Here is a short activity to apply what you just learned. Enter your response and select Submit. Time for an activity. Choose your response and then select Submit. This section is on bonding. Non-current carrying conductive parts of electrical equipment are required by Rule 10-600, Subrule 1, to be connected to a bonding conductor. However, Subrule 2 does not require non-current carrying conductive parts of extra-low voltage electrical equipment to be connected to a bonding conductor. Rule 10-602 requires a bonding conductor to be installed with each group of parallel conductors. When conductors are installed in parallel in separate cables, raceways, or bus. Minimum bonding conductor size in parallel raceways is shown in the diagram. The bonding continuity for service raceways, cable armor, cable sheaths, and all service equipment enclosures containing service conductors as required by Rule 10604, including meter fittings, boxes, or the like, must include threaded couplings and threaded connections to the conductive enclosures